So chapter 1 is on matter and change. So what's chemistry? Are there materials in your house that are related to chemistry? Like what?
Candles.
Salt, candles, milk, water, Clorox. Pretty a lot of stuff, right? Almost everything can somehow get related to chemistry. Because chemistry is the study of matter. So it's the study of the composition, structure, and properties of matter. So we're studying matter, anything that has mass and takes up space. So we're studying the composition, so how it's made up, the structure, and the properties. So that properties could be the physical and chemical properties of that matter. And we talked about, or we listed the branches when we did our outline, but let's see if this works here. Sometimes that pen doesn't want to work. Okay, organic. What is organic chemistry studying? Anything that contains carbon. So carbon containing. What's inorganic? What? No carbon, right. Anything that has no carbon. So without carbon. It's physical chemistry. They're looking at what? Okay, properties of changes. I'll put that. So we're looking at products and reactants and how are they actually changed in a reaction. Analytical chemistry, they study the composition of compounds. So what is it actually made up of? How many hydrogens, how many oxygens are in that compound? Biochemistry. If you studied biology last year, what was that? The study of life. So biochemistry is chemistry of life. So looking at how maybe food is broken down in your body, or how does hemoglobin work chemically to carry the oxygen. So the chemistry of life. Then theoretical, they're using chemistry to solve problems, like, and could be future problems. Areas with acid rain, maybe they are going to help solve some problem, like how do you prevent acid rain from eroding certain things using the chemistry behind it. Okay. Questions on those branches? Okay. I don't know why that one's blurry, but matter. Matter has volume and mass, so it has mass and it takes up space. So everything you see has matter, is matter. And we have atoms, elements, and compounds as part of the matter. But atoms, what's the atoms? Yep, the smallest unit. And it keeps its characteristics, like each atom can be different and different type, but if you break down an atom anymore, then you just get protons, neutrons, electrons. They always behave the same no matter what atom they come from. An element, it's an element.
Single type of atom.
Right, several types of, or several atoms of the same type. Right, it can't be broken down, and that's the simplest that it can be. Compound, made up of different elements, two or more elements combined together. They have to be chemically fixed, and you can separate those if you by chemical means. So you could break those bonds. Different elements, yep. Two or more different elements. You can break the bonds to break them down into elements. Okay, and then we have some different properties of matter. Extensive and intensive properties are both physical properties. So if you have a physical property, you can determine whether it's extensive or intensive. Extensive depends on the amount of matter present. So it depends on how many pens or the amount of water that you have. What would be an example of an extensive property? Yeah, but what property of that water would be extensive? Those are all just matter, but what property? Like, what can you measure about that water or that ice that would be extensive? The mass of it, the volume, and the mass and volume both change depending on how much water or how much ice you have, right? So those would be extensive physical properties. Now, what would be an intensive property? It's a property that does not depend on the amount of matter. What? The water boiling, the boiling point, doesn't matter how much water you have. It's going to boil at 100 degrees Celsius, right? It might take more energy to get up to 100 degrees Celsius if you have more water, but the boiling point is still 100 degrees Celsius. The color, doesn't matter how much water or ice or books or whatever you're looking at. Does color change depending on how much you have? No. Color's one. Density is another one. Melting point, yep. Okay, so those physical properties, they can be observed or measured. So all those properties that we talked about are physical properties. We just split them as, we characterize them as extensive or intensive. So a physical change is a change that does not involve a change in the identity of the substance. So change of state is a very common one. If you have ice and you melt it, ice is H2O, liquid water is H2O, right? Have you changed the structure of the compound? No. You've just changed its form, but it's still H2O. Or what about ripping your paper? Does that change the paper? No. It's still paper. Right. Now, if you burn your paper, is it still paper at the end? No. So that's different. So chemical properties is the substance's ability to transform into a different substance. So the actual chemical makeup of that compound has changed, its ability to change. So a chemical change occurs when that substance is converted to a different substance. So burning your paper, you've actually changed it. Rust. Rust is when iron reacts with the water in the air into iron oxide. So it actually changes. When silver tarnishes, that's a chemical change. You think of any other chemical changes?
What's it called? You know when you have like if you get a ring from
Oh, and they leave that green mark on your finger from a ring? Yep, that would be chemical. Digesting food?
What about a
Chemical?
tan?
A tan. Your body produces more melanin, and that's what makes you have a tan.
Chemicals.
So I'd say chemical. Because your body has to produce more. It's not actually changing your skin, though. I don't know. That's a complex one.
Maybe a hypothetical question.
Okay, so lots of chemical changes. So energy is always involved in these kinds of changes. And a lot of times it's in the form of heat or light. And that's usually for chemical changes, heat or light. That energy can be absorbed or released but not created or destroyed. And that's called the law of conservation of mass, or law of conservation of energy. So it can be absorbed, released. It can change forms. There's all kinds of different forms of energy. Heat and light are just two examples. If you drop your book off your desk, your book has kinetic energy, right, when it's moving through the air. When it hits the floor, does it bounce back up with the same kinetic energy? No. So does it lose energy? Energy can't be lost. So where does that energy go? It gets transferred some to the floor. It can be transferred into heat. I'll bet that the temperature changed a little bit around it. It can sound as an energy form. So you hear a thud. That would be a change of energy. So your energy can change forms, can be absorbed or released from one substance to another, but it cannot be created or destroyed. And then here's 4 evidences of a chemical change occurs. We will probably see this we will see all 4 of these in labs that we do. So A is when acetic acid, which is vinegar, and sodium bicarbonate is baking soda are mixed. The solution, what happens when you mix those two? You form bubbles, right? And if you have too much for the container, then it overflows. But you form bubbles. B is when a precipitate forms. When you have 2 in our labs, we'll call a precipitate a solid that forms when 2 liquids are mixed. So you see there's a clear liquid in the test tube, there's a clear liquid in the beaker, but when they mix, they form this yellow precipitate. Now that doesn't mean the whole beaker becomes one big solid yellow piece. Okay, if you let it sit for a while, that yellow will settle out. You'd be able to filter it out. It's a solid that you could take out of that liquid.
It's the stuff like it's like mushy, and then when you squeeze it, it turns into solid.
Cornstarch and water? Yeah. Okay, aluminum reacts with iron oxide in a clay pot, and it releases energy in the form of heat and light. So we'll see heat and light. We'll do a flame test at some point where you'll burn some different compounds. And then at the end of the year, we'll do some reactions with acids and bases, and phenolphthalein is an indicator that tells you when there's been a change in pH. So when you add acids and bases together, they can neutralize themselves to a pH of 7, and the phenolphthalein changes color. So a color change is an indicator. Okay, classification of matter. So matter can be broken up into pure substance or mixture. A pure substance will be either an element or a compound. So if you have pure H2O that's been distilled and run through a reverse osmosis, that would be pure H2O. That would be a pure substance. Now, if it's just tap water, is that a pure substance? No. There's different ions, minerals, and stuff that's in that water. So that's actually a mixture. which is why when we do labs, use the water in those plastic carboys, they're called. That's sitting by JD. Okay? Don't use tap water. Mixtures can be separated, and we have two different types of mixtures, homogeneous and heterogeneous mixtures. So mixtures are a blend of two or more kinds of matter. Homogeneous are uniform in composition. So example solutions, soft drinks, Kool-Aid. Yep, those are all homogeneous mixtures. Heterogeneous are not uniform throughout. Orange juice with pulp. Eventually, the pulp settles to the bottom, right? So that is not that is heterogeneous. The floor. Look at the. If you take one square, does that look exactly like the other square? No, it's not uniform. Chocolate chip cookies. Salads, those are all heterogeneous. So this just is a diagram that splits it. The matter can be split into pure substances or mixtures. Pure substances are either elements or compounds. Mixtures are homogeneous or heterogeneous. One thing that is different between the pure substance and mixture also, pure substances cannot be broken down by physical means. You can't separate them with physical means. Mixtures, you can separate them. Even salt water. Salt water is a mixture, right? Would it be homogeneous or heterogeneous? Homogeneous. Can you separate the salt from the water? Yes. So you can still separate that. Heterogeneous mixtures, usually it's pretty easy to pick out one part of the mixture from the other, unless it's like hard tile or something, but you can pick it out.
Separable.
Yes, both of them can be separated. Okay, compounds are elements. We talked about that. They have the specific characteristic properties. So all water will have the same properties so that you can determine what compound it is based on the properties. And they have the same composition. H2O is always H2O, not H2O2. You don't want to drink H2O2. You guys know what H2O2 is? Hydrogen peroxide. Okay? So just by adding oxygen, you have hydrogen peroxide, and you don't want to drink that. Do they? Really?
Yeah. It says on the bottom, use it as a gargle or mouthwash.
Really? Ugh. That'd have to taste horrible.
Probably.
Yeah, we already talked about examples of those mixtures. The last part of this chapter was about the periodic table and how it's organized. So we will look at that. We have the groups or families are the vertical columns. So we will usually call them groups. So group 1, 2, 3, 4. They all have similar characteristics. So in similar properties, whether or not they are able to burn, if they're able to rust and react with different compounds, they would be similar. Periods, horizontal, going across. So there's different types of elements. The metals are, I'm going to put this on there. So they're left of the stair-step line. If you draw a line, and I don't know if yours has it, but on this periodic table, you go across, you go down, you start right under boron, go across, down, and make a stair-step line. Anything touching that line is on left of that line would be metals, and then non-metals over here, and then we'll talk about the metalloids also. But metals have metallic luster. What does luster mean? They're shiny. Yes, sparkly, shiny. They reflect light. They conduct heat and electricity. They are solid at room temperature, except for what metal is a liquid at room temperature? Mercury. They're malleable. What does malleable mean? You're able to shape them. You can bend them. You can pound it into thin sheets. Ductile. Well, that's why they use them. They can be pulled into thin wire. Ductile means they're able to be pulled into thin wire, and they're used then to conduct electricity. There's a couple special groups of metals. The alkaline metals are in group 1, and the alkali earth metals are group 2. Here's just some pictures. There's gold. What do you think B is? Copper. C? Aluminum. Yep. Types of element, or the other are nonmetals to the right of the stair-step line. And they can be solid, liquid, or gas. They're brittle. What does brittle mean? Easy to break. If you bend it, they're not bendable. If you try to bend it, it's going to break. They have low conductivity, and there's a lot fewer nonmetals than metals. And there's a group of nonmetals that are special called the halogens. It's group 17. That's fluorine, chlorine, bromine, iodine. They're the group 17 halogens. Here's just some picture. You can see they all look different. These are all solids at room temperature. And then the last type is metalloid. And the metalloids are right on the stair-step line. And they are kind of transitional, where they have some properties of the metals and some properties in the metalloids, or the nonmetals. So they are solid at room temperature, but they're semiconductors. So they can conduct electricity, but not nearly as well as the metals. And the last noble gases are group 18, the far right group. They're generally unreactive. Do you remember in physical science when you talked about octets and the outer shell needing 8 electrons? And do you remember that kind of? Well, we'll talk about it in more detail later, but that's why they're unreactive. They have 8 valence electrons already, and so they do not need any more. They don't want to give away any of theirs. And they are all gases at room temperature. That's why they're called noble gases. Any questions on those? Yep.
What was malleable and
Malleable